can move on to the next talk. So a warm welcome to Sarah Dean. Thank you for being here today. Sarah is currently an assistant professor in the computer science department at Cornell University. She has recently completed her PhD at UC Berkeley, and she was a postdoc at the University of Washington. Sarah is interested in the interplay between optimization, machine learning, and dynamical systems, and she authored a number of foundational works in this area, in data-driven control and dynamical systems. She also studies applications to robotics and recommendation systems, and today she's going to tell us about feedback dynamics and safety in machine learning systems. So we are really looking forward to your talk today.
Great, thank you. Thanks for the kind introduction, and also thanks so much for the invitation. Should I try my video on one more time? Okay. All right, before I start, there we go. I think that I'm okay. Great.
Should unmute yourself.
I think.
It's okay.
Yeah, I think great. So yeah, today I want to talk about something that I think motivates a lot of the people who are listening. I'm not going to unmute, I think. No. Yeah, anyway, something that I think is relevant to all of us, like the general class of application domains that many of us care about, could be described as large-scale automated systems. And traditionally, these are things that look like warehouses, manufacturing, chemical plants, perhaps. And they're very important in like our modern technological society that these things run well. But if we think about the large-scale automated systems that impact us today, these also include things like news feeds on social media, e-commerce, and in general, the ways that we interact digitally using our smartphones and other devices. So something in particular that I want to focus on is ways in which this automation is enabled by machine learning, since this is maybe particularly true of these kind of bottom three domains. Now, of course, there's many differences between maybe the top row and the bottom row here, but there's also some similarities that might be useful to think about. Both situations make use of feedback, measurements, or information from the world in order to make decisions, automated decisions. There's also arguably some type of dynamics underlying these processes, although maybe better understood on the top row in physical and engineered systems and on the bottom row. Somehow this evolution over time of behaviors and preferences seems to be relevant in e-commerce or in newsfeeds, social media as well. And one question that I want to raise and talk about is the question of safety and what we do to build things responsibly as engineers. I think it's kind of ingrained culturally to think about these maybe engineered systems in the top row from the perspective of safety and responsibility, and maybe less ingrained on some of these applications in the bottom row. But perhaps, let's say, the issues clearly call for some perspective around safety and responsibility. So that's kind of what motivates my talk today. Let me just review what is machine learning and then why is it part of a feedback system. At the high level, machine learning is this process of taking a bunch of training data and generating a model, which can then automatically make predictions on the basis of observations. So for example, a machine learning model might look at an individual's history of movie ratings in order to predict how much they will like a new movie that came out. Generally, the training data and these new observations come from some environment, whether it's users on a movie recommendation platform or otherwise. And in the machine learning perspective, at least supervised learning, that's the end of the story. But if we take a systems level perspective of what happens here, it's certainly not. In fact, the predictions made by the model are often used in some type of policy to take an action on the very environment on which we got data from or we're seeing predictions, right? If this wasn't the case, there would basically be no point in designing the model in the first place. So this is, I'll argue, almost always relevant when thinking about machine learning systems. And what are the dynamics here and why do they arise? I want to make a distinction. Some of the dynamics arise because the actions we take impact the world, right? Sometimes we are directly changing the world via an action from a machine learning-based algorithm. But there's also dynamics that arise just because of additional data collected impacting the model and therefore the policy, right? So there's sort of these two types of impact that both cause changes over time. So today I want to focus on specific examples inspired by the setting of recommendation systems to discuss what these dynamics look like and what their implications are. I'll start with kind of maybe the lowest level, zooming in on the idea of a single user interacting with the system. And I'll talk about a relatively simple model of preference dynamics, motivate why it's of interest, and then what its implications would be for algorithm design. Then I'll zoom out a little bit and think instead about populations of users interacting or choosing between many different systems, and how this process can also give rise to dynamic behavior, and the implications there in terms of maybe fairness or welfare. And then kind of briefly towards the end, I'll go through some of the challenges towards defining safety or ensuring safety in systems like this. These first two examples are kind of maybe technically very precise systems, but there will be gaps between what I can describe and what is probably going on in the real world. And I'll talk about that in the third part and the challenges that we might have to solve there. So first, I'll start with the setting of preference dynamics. The basic idea here is that interests, an individual's interests, might be impacted by recommendation. So we have a recommender policy, there's some machine learning algorithm along with maybe some ranking algorithm to generate content to display on a web page. This content that is recommended is then observed by a user, interacted with, clicked on, rated, watched for some amount of time. And many of those behavioral activities are recorded and then sent back to the recommender policy as an express preference, right? So this is maybe our classic feedback loop. And if I want to continue with this perspective, I can even say actually the choice of recommended content is an action A or control input U, but I'm using the action state notation here. The user potentially being impacted by this content, is affected by an update to the internal state. So the state is now updated depending on the previous state of the user as well as the action taken in terms of recommended content. And then the preference that is expressed is some function of the state and the action. Now, this is obviously very general, and so I can't really say anything more about this. I'm going to look at a very particular model of this system. The first thing I'll do is fix my observation model as an inner product model of the representation of the user state and some representation of the content that we've selected. This model actually underlies some of the most foundational and arguably still state-of-the-art methods in recommendation, which are based on matrix factorization. Just to briefly say what this is, suppose I have a whole bunch of users as well as a whole bunch of maybe movies to recommend. Underlying this, I have an idea of how each user would rate every single movie. That's this dense purple matrix. And for various reasons, I might want to model this as not just an arbitrary matrix, but a low rank matrix to encode the fact that there's structure and correlations between the movies that people like. And so my overall matrix of all users' preferences for all movies might be factorized into something that represents all the different users times something that represents all the different movies. So that, for a given user and a given movie, the rating is, approximately well approximated by this inner product. So we're not going to do matrix factorization in my talk today, but just to say that that's where this inner product model is coming from. So then that kind of leaves us as a question, how do preferences change as a result of an action? I'm going to look at a very particular model that is inspired by the phenomenon of biased assimilation. So biased assimilation is the idea that an opinion or a preference, let's say an opinion that you agree with, if you think that it has kind of the right, if it sounds right to you, the argument makes sense, you will agree more with that person. But if you disagree and you think it's completely nonsense, you will agree less with the opinion. In terms of preferences, we could say that if you really like something, you like it even more after seeing it again. Like familiarity increases your enjoyment, whereas if you really hated it, you really definitely don't want to see it again, right? It kind of amplifies that reaction. So let's formalize this a little bit. In this inner product model, I am kind of implicitly representing my actions, which are part of some action set, as being d-dimensional vectors. And for simplicity, I'm going to assume all vectors are unit norms. So this is part of the d-dimensional, the sphere in d dimensions. Because I have this inner product model, I'm assuming that the state of users lies in that same space, right? So preferences are also d-dimensional vectors with unit norm. Now let me explain the mathematics of this model that I have on the screen and why it, it shows us the biased assimilation update. In this model where user preferences are represented as vectors, what really matters is the direction of the vector. That kind of tells you how much somebody will like a given movie, particularly the alignment between their preference and the movie that you recommend. And so this update equation says that the update to the initial state, to the state at time t, is in the direction of the recommended movie. So my representation incorporates a little bit of the representation of the movie that I saw, but the coefficient is proportional to the affinity that I have for that. Let's say inner products represent ratings or affinities, right? So we see that affinity not only governs what an algorithm observes from this process, but it also governs the update to the state. So to make this, to kind of illustrate this phenomena in a simple setting, let's say that I have a music recommender, and let's say that there's just 2 dimensions here. Maybe this person likes music depending on its tempo and the lyricism, the beauty of the lyrics. And I think this person, kind of equally likes these 2 things: fast music with good lyrics. So if the music recommendation system recommends something pointing purely in this direction, which let's say is just the fast tempo direction, kind of average in terms of how poetic the lyrics are, this is saying the user will kind of shift the preference towards that, to say, yeah, I'm really into this high tempo stuff right now. I actually prefer high tempo because I listened to the song that I liked, and what I liked about it was the high tempo. On the other hand, this model also posits that if I recommend something completely opposite, an extremely slow song, that will actually spur the user to say, okay, I really want a fast tempo song now. Like, that was horrible. I don't want anything slow like that again, right? So there's kind of this, this very simple nonlinearity in the effect of actions, where actually an action and its negative have the same effect on the user preference. And so this model was first proposed, so I guess I should say models of bias assimilation have been around for a long time, but this particular kind of vector model was first proposed, as far as I'm aware, by Hasla et al. In 2019 as a model of opinion dynamics to kind of investigate how people's opinions about maybe hot button political issues form and are impacted. And in that work, the focus was on polarization. And how bias assimilation can give rise to polarization. In particular, they study a model where there's a population of users following these dynamics, but where the actions A are generated randomly, but are the same for every user in the population, right? So identical stimulus for everybody, but generated randomly. And they show that this leads almost surely to polarization, which is where, let's say, a population has initial preferences in all different sorts of directions, or in this work, it was initial opinions. But after seeing this stimulus and either being attracted to or repelled from these ideas, we end up with a population who is either extremely in agreement with one idea or extremely in disagreement. There's sort of 2 poles. And in these dynamics, because you have a random stimulus, there's actually, what the opinions are will keep changing, but what's constant is that there are 2 opposing ones. And follow-up work kind of extends the model to slightly different, slightly less linear versions of these dynamics that still capture the same idea and show that the same thing holds. So I'm concerned with personalized recommendation, right? How does the story change when we're actually targeting individuals with content that they'll like? And what does a model like this mean for algorithm designers? So maybe one thing to note, kind of a very simple observation that essentially leads to all of our results, is that if you fix a recommendation, so my action is just fix that A for all time. Let's say I'm recommending maybe not the same song, because that sounds a little bit too simple, but like the same artist or this from the same playlist at all times to a user. This model says that their state actually has a closed form solution that is a linear combination of their initial states, their initial preference, and the vector representing whatever I'm recommending. And the coefficient on this first term is positive and decreasing. So the impact of the initial state decreases over time. And the coefficient on our second term, the representation of our action, is increasing in magnitude, and it's the same sign as the initial inner product. In other words, the initial affinity. So either someone is being driven towards loving high tempo music or away from low tempo music, right? Let's say, to go with this example. So it's kind of a simple idea that these dynamics allow you to bring somebody's preferences in any direction that has an initial positive inner product. As long as there's an initial positive impression of a piece of content, then that a person will continue to enjoy consuming content like that. On the flip side, if there's an initial negative reaction, the opposite things happens. So I won't go into kind of the theoretical results or like the low regret algorithms that you can develop in this setting. I'll just tell you kind of the two implications that come out of this. One is that it's not actually necessary to identify somebody's preferences in order to make recommendations that have high affinity or achieve high ratings. Right? The reason is I just need to have a rough understanding of the direction that somebody's preferences are in, and then I can just actually make them learn to love what I have to recommend. That's one implication of this. So as much as we think that online machine learning and data is so important, maybe we're not learning anything at all. We're just learning approximately close enough to get relatively addictive behavior or something out of users. And the other implication of this is that whatever content it is that I'm generally recommending to somebody, their preference will collapse towards that content, right? Kind of lose their initial preferences and will just end up kind of mirroring what I, as a content recommender, have to offer them. So to put this in a big picture in terms of a population of users, it's not so much polarization that we have to worry about, which is this picture here. Polarization comes up in the context that everybody sees the exact same content and either really disagrees or really agrees. That's not really an issue if we personalize, because we don't have everybody reacting to exactly the same content. Instead, though, maybe we have some kind of local polarization or local preference collapse where people are drawn towards whatever is convenient to recommend to them, and that's where they land. In the paper, which I have a full citation at the end, we show that that is kind of the conclusion of these high rating strategies, but it's not inherent to these dynamics. If we propose a kind of a simple randomized algorithm for randomizing over several pieces of content and show that it's possible to exactly preserve somebody's preferences. And so it's by no means kind of inevitable that you would have this collapse. But that the randomization strategy is a bit more complex, and it does require identifying not only the user's initial preferences, but the correct vector representations of all the items, which we don't actually solve, but we do state that you would need to know them. So kind of to summarize what I have to say about this, these biased assimilation preference dynamics actually make it easy for an algorithm to achieve high ratings. But they risk mode collapse in individual preferences. They risk kind of a, let's say, a collapse of initial diverse range of preferences into whatever content is easy to recommend. But they do not really risk polarization. Some open questions that I hinted at is, what if you wanted to do some smarter planning on these types of dynamics, but you actually don't know the representations S and A. So far, I've just analyzed what happens in terms of the preferences S and the representations of the items A. But in classic recommendation settings, neither of these things are known, and they're just learned from data. And they're not actually even uniquely determined by data because you have kind of a rotation and variance. Also, what if the dynamics maybe are not quite as simple as I showed, but have some unknown parameters to them? Maybe individuals have some stable preference that they will tend to move back towards. How would you learn that? And how would you design recommendations in the presence of that? Another open question kind of at this level of modeling, of course, is there's certainly other phenomena that impact dynamic behavior of users on recommendation platforms. For example, one that's maybe a elephant in the room is the notion of satiation or boredom. Obviously, if I recommend the same song to somebody over and over again, they don't love the song more and more. They actually hate the song and would never like to hear it again, right? So there's some other phenomenon happening. Additionally, inconsistencies. Sometimes people will click on things they don't actually like. So how do we model that kind of misalignment in the measurement? I think these are all things that could be extensions to this type of vector modeling on preferences. But I want to move now to the second topic, which is participation dynamics. And one of the motivations for doing this is that, maybe you do think that people's preferences can be changed as long as you get the right direction of vector, but maybe you actually think people aren't that simple. We have preferences, they're relatively static. Or at least if they're not static, they can't be exactly controlled by an algorithm. And I concede that point. I think that that is true in a lot of cases. So even when preferences are immutable, populations as a whole still might be susceptible to segmenting or targeting based on maybe fixed preferences. So that's kind of the motivation for this next topic. And here I'm thinking of a setting where individuals choose to participate in different online platforms, different learning-based services, depending on the accuracy. So for example, I might use Spotify because I think that it has better playlist generation compared to Google Music. And just a very simple example, let's say that there's sort of, roughly two subpopulations of individuals, right? And I'm in the setting of linear regression. I want to predict how long somebody will listen to the next piece of music based on the last song they listened to, or something simple like this. And maybe actually the data looks very much like this, so there's actually not a good single linear fit, because there's kind of two different clusters of people who have different linear relationships. If I maybe wanted to try to catch everybody, I would have a line that looks like that. But let's say that I maybe start out, or for various reasons, have a lot more participation from that lower population of squares, right, of population 2. Then I will learn a regression rule that favors that population just by doing standard kind of risk minimization, the bread and butter of basically all machine learning. And over time, that will cause the first subpopulation to stop using my system because I'm not really good for them. As a result, there's a self-reinforcing feedback loop between these participation choices and retraining, right? Naive retraining by a learning service. And these dynamics, or a version of these dynamics, actually, yeah, this version of the dynamics was proposed by Hashimoto et al. In 2018 in the case of just a single learning system. And it was used to kind of investigate the idea of representation disparity as a notion of fairness. So how minority populations might have errors amplified over time and essentially be poorly served by these services. I now want to look at maybe a multi-learner perspective where users are not just choosing to participate or not, but actually spending their time choosing to spend their time among different services. So let's say here that I have 3 subpopulations. In general, I'll have n. And for the sake of simplicity, let's say each subpopulation is actually just one person who's spending different amounts of time between these 2 different music services. They are choosing a participation value, alpha. Each subpopulation I chooses an alpha for each learner j, right? And summing over j, there's some fixed amount of budget time budget that each of these individuals has to spend. So for example, this first user might mostly use, I don't know, music service 1, but sometimes they use music service 2 to just find a little bit more music discovery. And now at the same time as that's going on, these services are observing user behaviors and learning from that data. And we're going to suppose that they're kind of myopic and yeah, they're myopic learners. They're not doing a lot of smart planning. They're just looking at who uses their services and minimizing loss over those individuals. So for example, okay, sorry. Oh. For example, you know, I might actually have all 3 of these users using this first learner to varying degrees, and therefore the parameter that this learner uses will maybe actually favor this bottom user, even though there's a lot of participation from the top user, right? So in both cases, what I describe, the participations and the learned parameters of a machine learning model, let's say, update according to a risk function, which is kind of an expected loss over the population, where each subpopulation favors learners with lower risks, and each learner reduces the observed risk, averaging over their users. So we study a kind of generic version of these dynamics, where we only need to assume that each of these entities are risk minimizing in the limit. And what that means is if I held all of the learners constant, each subpopulation would eventually converge all of their participation to the minimum risk learner. And if I held all of the subpopulations constant, each learner would eventually converge to the risk minimizing parameter, right? These are fairly mild assumptions. Things like gradient descent would satisfy this. Now, again, looking to our linear regression example with 2 populations, let's suppose I now have 2 learners. And initially, you know, both learners might be kind of catering a little bit to both populations, but not exactly in the same way. And so over time, through this dynamic, we would see specialization, where one learner specializes to subpopulation 1, and the other learner specializes subpopulation 2, as the participations, which I denoted by shading, kind of also specializes to each service. So this is not something that just holds for the simple linear regression example. We can kind of generalize this intuitive type of equilibrium. First, actually, to make this formal, I have to assume that the risk function, so the expected loss, so for example, in linear regression, I would have a squared loss summed over all data points. I have to assume that those are strongly convex. And then I'm going to define kind of that phenomenon we just saw formally, which is a split market, where each subpopulation I allocates all of their participation to a single learner, which I'll call gamma of I, right? So each subpopulation is fully sold on one of these services. So we can show that an equilibrium of these dynamics will, first of all, given the participation alpha equilibrium of all subpopulations for all the different learners, it must have that the parameters of equilibrium minimize this kind of average risk over all learners and all subpopulations, averaged by the amount of participation, right? This is kind of like the total risk that's going on, the total amount of misclassification, roughly. This is actually just a direct, this just directly follows from the strong convexity and the risk minimizing in the limit setup of the dynamics. More interestingly, we can say that these equilibria are asymptotically stable if and only if the allocation is split market. So the only stable equilibria have to be split market equilibria, where individuals are kind of all in on one of the services, one of the learners, each as a subpopulation, I guess. And no subpopulation prefers to switch. So at the equilibrium point, there's no subpopulation who says, oh, actually, that learner is more accurate for me, I'll switch to them, right? And this is kind of the full characterization. These asymptotically stable equilibria exist, but they're definitely not necessarily unique. And so what is the meaning of this? Like what does that imply in terms of fairness or welfare? Like these dynamics were initially introduced to motivate concerns of fairness, right? Where let's say that there's a utilitarian notion of welfare that is inversely related to total risk, where total risk is just summing up the risk. This is kind of like on average, how many misclassifications are there in our full population? Whereas a notion of fairness is the worst case risk over subpopulation. So instead of average, you consider the worst case. So they say good and bad things about these dynamics. The good thing is that the stable equilibria are all local maxima of the social welfare. Let me point out that the social welfare function is not convex because we have this multiplication of participation and the risk function. Right? So it's not convex. It might have many local maxima, but they are the stable equilibria. So that's kind of good. That means that these dynamics are doing something kind of reasonable with respect to a utilitarian notion of welfare. But one bad thing is that it's not necessarily the global max, and in general, it's actually NP hard to find this global max. Actually, we can see this by making an analogy between these dynamics, which we think might arise in reality, and clustering algorithms, which follow kind of a k-means clustering, would follow very similar dynamics. And we know that problem to be NP hard. Another kind of downside, or another not so great news, is that utilitarian welfare is not the same thing as fairness. And so having low utilitarian welfare, even if we could get to that global max on welfare, does not guarantee that the worst case subpopulation has low risk, right? You can have very small minority populations who don't contribute much to the average, but experience very poor accuracy of machine learning models. But the good news is that increasing the number of learners, so kind of adding an additional learner to the setting, will always decrease risk and increase social welfare. So there is at least one kind of quote unquote natural mechanism that allows you to move forward. To summarize, these risk minimizing participation dynamics lead to segregated equilibria, which locally maximize social welfare. Now, whether this is desirable or not probably depends on the setting. Maybe you actually don't want services to have kind of monolithic user bases, and you think it's actually important for people to use services that are shared by people who are not like them. So this doesn't mean that we should let everything run as it goes, but this is what we should expect to happen. Some open questions involve things like finite sample effects. So in particular, how these lead to switching costs. For example, if a new learner enters the market, we kind of ignore finite sample effects and assume that they can immediately minimize risk. But in reality, they only have a little bit of data. It's going to be hard to have an accurate, useful model if you're not a large tech giant. Also, we could consider alternative learner or subpopulation dynamics. It would be natural for the learners to be in competition with each other in trying to capture market share. And it would also be natural for subpopulations not to just update based on the own risk that they experience, but perhaps on some network effects of who they talk to and what their friends think are better services. Okay, so I'm almost out of time, but I do want to take the last minute, 5 minutes maybe out of your coffee break to just say, what are the challenges in thinking about machine learning, human-facing systems this way? What are our challenges to making them safe? So one that I think is relatively easy to address from a technical perspective, but is still very pervasive, is there's actually an absence of an interface to a lower level controller that can take care of some of the details for our higher level goals. For example, most algorithms tweak rankings, tweak the content that they show in a very ad hoc manner, right? Sometimes there's actually kind of conflicting re-ranking or ad hoc score adjustment algorithms that are used to achieve additional goals. And these high-level goals include things like exposure, diversity, fairness in a recommended list. And there's really just not a standard abstraction from that high-level goal to this kind of low-level ranking algorithm. And to make an analogy, it would be like if we were flying airplanes by sending voltage commands. Okay, I know airplanes don't actually run on electric motors, but let's say you have a drone and we're sending like individual voltage commands to each of our motors rather than higher level thrust and pitch and roll and yaw commands. The second challenge is somewhat related in that part of the reason we can map motor voltages to understandable physical phenomena is because we know the dynamics of these systems because of the laws of physics. In recommendation systems, there's sort of unknown dynamics in many of the cases. Despite the fact that I told you about some models of dynamics today, we don't know how much those are true or what other phenomena we have not yet modeled. And maybe more importantly is that these dynamics arguably have limited controllability. It's not so much like flying an airplane as it would be trying to fly an airplane in a huge hurricane, right? People's preferences are maybe, and more generally social dynamics are maybe not mostly driven by factors in the control of algorithm designers, especially for any single system. And I would argue nor should they be. Despite this, I don't want to kind of give a carte blanche to large tech companies that are kind of playing around in our social world. I do think that despite these issues, there are ways that we can intervene in these systems. Airplanes, for example, have all sorts of backup systems, backup generators, and ways that even in a hurricane, you could do your best to avoid crashing. I don't think the same can be said about the way that negative phenomena or rumors can currently spread in our social media. And then the third question, and kind of a foundational and very important one, is, what are the harms? What are we trying to avoid here? And who decides on what they are? Human values are pretty indeterminate. They may not be agreed upon by everybody, and they're very hard to formalize. I don't think that means we shouldn't attempt to build algorithms that kind of achieve our values. But it does mean that it's important to constantly address and think about this gap between the social world and the technical interface and abstraction, and allow for that gap to be kind of bridged through community feedback, democratic governance, education, all of these things. I think I'll say that in general, facing these challenges includes both rich technical problems, which folks in control and automation are well posed to handle, but also really important to consider interdisciplinary perspectives. And I just want to credit all of my collaborators on the different topics that I talked about today. These first two sections were with several folks at UW, as well as several collaborators on the interdisciplinary side who've helped me think about these challenges to formalizing safety. With that, I'll thank everybody, and I guess maybe take questions now or after, I'm not sure. Okay.
For the very nice talk. We have time for a quick question now, and maybe we can continue during the panel discussion. Is there any question from the audience?
Yeah, thanks very much. Sort of an interesting point of view. I noticed that a lot of the dynamics evolve to cases where the recommender basically gets a group of people, or you lose rank in the recommender system, and you end up with a sparser set. And there would seem to be a strong economic correlation to those results, which would force recommenders to try and get the most valuable customers, or peddle the cheapest films to the most number of people, if you like. How do you see correcting for fairness in those situations?
Yeah, that's a very good question, right? I didn't explicitly analyze like who's the most valuable customer or which content is easier to recommend, but it's sort of easy to see how that would really alter these. I think that one answer is that that effect is most prominent when there's kind of this single system at play where, people, like in a recommender system, there's just one recommender system that's kind of peddling out in content, or there's just this one kind of idea of a market between users and maybe non-competitive platforms. So I think kind of moving to like more decentralized settings to some extent might make that better. Also thinking about who are the producers and like what are their incentives. In a lot of cases, actually like this word prosumer from the energy setting, it actually also applies in maybe content settings as well, where users might feel like they have a opportunity to create content, even if it's not as economically viable as somebody who's motivated primarily by market goals. And so I think that's another possibility.
Right. Thank you. We can move on to the coffee break.